We pick back up with question 36, and they're asking us to put these marked elements in order of increasing electronegativity. Electronegativity is how hard you can tug. We know that in general, smaller atoms are better at tugging electrons to them. Why? Because their nucleus is closer to the electrons they are tugging on. So in general, we look for smaller atoms. We look for the atoms that need electrons the most, because why would you pull on electrons if you don't need them? The family that needs electrons the most are the halogens. If they can get one electron, they satisfy the octet rule. Number 2 is marked right here. Fluorine needs an electron very, very much. What happens to size as we move left to right across the periodic table? It gets smaller. So fluorine is very small. You're like, but wouldn't neon tug harder? No, neon doesn't need an electron. Fluorine will tug very hard, and it is smaller than oxygen, which is right next to it. So the hardest tugger is going to be in the upper right. Fluorine has the highest electronegativity of them all at 4.0. So we're looking for the list that has number 2 leading off, or number 2 being last, because we're putting them in order from lowest to highest electronegativity. Fluorine's going to have the highest electronegativity of them all at 4.0. So which of these lists has a number 2 last? The only one that has a 2 last is letter D. All the other answers would be eliminated. Who would have the second highest electronegativity to make sure D is correct? Well, oxygen is right next to fluorine, so it is also very small like fluorine, and it also needs electrons. In fact, oxygen needs to tug 2 electrons to it, not just 1. So oxygen's in the upper right. The ones in the upper right have the highest electronegativities. They're small and they need electrons. So oxygen would be the second highest electronegativity of them all at 3.5. So oxygen should be second from the end. We want the smallest first. So we start going this way. There's no other elements, but the next element we see is in the row above it, number 3. Silicon. Silicon is in the row below it and to the left, so silicon would be less than fluorine and oxygen. How much would it be? Well, it turns out silicon's electronegativity is 1.8. As we continue moving to the left, the atoms are getting bigger. And in fact, underneath, the row underneath it, all the way to the left is calcium. Calcium should have the second lowest electronegativity of that group, of that pairing. It should be the second one listed. And if we look, calcium's 1.0. Then still further to the left, and now 2 more rows down, is the element cesium. Cesium is way down here. It has one of the lowest electronegativities of them all. It is 0.7. So cesium should be first. Number 5 should be first. 5, 4, 3, 1, 2. And as we see here, all of that I just mentioned is written out for you. We move on to the next question. Number 37. What best explains why nitrogen has a positive affinity? Nitrogen has a positive affinity. When we look on this list right here on electron affinities, we can't even see nitrogen right here on this thing. Nitrogen is way down there. There's phosphorus. Nitrogen's tucked up underneath there. Nitrogen actually has a positive affinity. Right around 0, a positive affinity. Why is that? What these reasons would best explain it? Well, nitrogen's half full. Half full offers some stability, as we learned, like what factors contribute to electron affinity. If we kind of advance to one of the last questions right here on this test, number 40. Which of these things affect affinity? Nuclear charge. The more protons you have, the easier you are at pulling electrons to you. Higher nuclear charge, higher affinity. Size also matters. Size also matters. How does Size matters. The smaller you are, the better you are at pulling electrons to you. So small radii have higher affinities. What about electron configurations? That also matters. And as we see here, a half-filled P, D, and F contribute to stability. And the shielding effect. The greater shielding effect you have, the less you are able to attract electrons to you because the inner levels are getting in the way. So all four of these factors contribute to affinity. And we know that, as it said on the third one, letter C, a half-filled P offers some stability. And if you try to give an electron to nitrogen, as we can see in the configuration right here, 1s2, 2s2, 2p3, as you try to give an electron to it, that electron is going to be going into an orbital that already has one. So that electron is going to try to repel the electron out, meaning you have to add more energy to it to squeeze it in. When you have to add energy to it, your affinity goes up. And in fact, nitrogen, you have to add energy to squeeze it in there, letter A. All these other factors are not even true. Nitrogen's electron is made more stable. No. It's made less stable. It's made less stable. And if it was made more stable, the electron affinity would be negative, not positive. It's not made stable. It's made less stable. Nitrogen has a large radius. No. Nitrogen has a very small radius. Nitrogen's radius, we're looking up here. When we're looking at nitrogen, it's on the right side of its row or whatever. And when we look at the radius, look at nitrogen. It's way over here. It's a pretty small atom. Small atoms tend to have higher affinities. But the reason nitrogen doesn't have a high negative affinity is because you're trying to squeeze the electron into the already half-filled P sublevel. Electrons are positive charged. No, they're negative charged. That question's wrong from the get-go. Nitrogen's a nonmetal. Yes, it is. And nonmetals have positive affinities. Look, no. Look over here. These are all nonmetals right here. These have big negative affinities. The reason these columns are so large is they have large affinities. Nonmetals need electrons to get stable. 38. Which of these equations is incorrect? Positive affinity means we have to add energy. There's the energy we're adding to get an atom to take an electron. So we're adding an electron to an atom. If it's a positive affinity, we got to give it energy to take the electron because it didn't want it. The stability went down, so we had to add energy to get it to take it. On our little chart right here, our little teeter-totter, if it's not stable, if it's lowering stability, the energy goes up. You have to add energy to get it to take it. So that equation is correct for a positive affinity. Ionization energy is the energy you add to an atom, correct, to get it to pull the electron off. So yes, we're pulling an electron off. But if you pull an electron off an atom, it leaves the atom positive. The equation that we saw was negative. This would be the correct right side of the ionization energy. Letter B is fouled up. A negative electron affinity. Well, we have an atom. Affinity is the measurement of the energy change when we give it an electron. When you give it an electron, it does become minus. But you can also write the energy change this way. Change in energy or change in heat is negative. It's giving it off. Or you could put the energy right here, plus energy. Either of those would be correct for a negative electron affinity. What about letter D, second ionization energy? Second ionization energy is the energy required to pull off a second electron. So we start with a cation. It's already removed one. And we add energy to pull off a second electron, leaving the ion 2+. That's correct for second ionization energy. First ionization energy is the energy to pull off one electron. That equation would look like atom A plus energy makes A plus the electron. That equation we had already saw on number, 17? Or was it number 18? Hold on. Question number 17. Ionization energy equation is right here. The equation illustrating the removal of an electron. Atom A plus energy to rip the electron off. There's the electron we ripped off, and we're left with a plus, a cation. When you take off something negative, you leave something behind that's positive. All right, that's number 38. 39, they gave us 3 dot diagrams. X has 1 dot, Y has 2 dots, Z has 7 dots. And we are told their main block. So what does that tell us? Well, X, since it has 1 dot, group 1, family 1. Y, since it has 2 dots, must be in the S block, column 2, group 2, family 2. Letter Z here must be a halogen, 7 valence electrons, family 7, Roman 17. And they're saying which of the following statements is false. Atom Y would have the lowest electron affinity. Absolutely. Y already has 2 in the S. If we give it another electron, it would have to go into the P sublevel. The P sublevel has more energy than the S, so we would have to add energy to get it to go into that P sublevel. And S2 was already partially stable. That would mess it up. We've kind of talked about how family 2 really doesn't want an electron. If we give one to the halogen, it would definitely want it. We would satisfy the octet rule. If we give one to X, it would want it a little bit because we would fill up that S sublevel. And 2 in the S is better than 1 in the S. Atom Z would have the highest ionization energy. Well, they're in the same period. So Z is in group 17, family 7. Z is way to the right. It would be way smaller than X and Y. Z would definitely be smaller. It would take more energy to strip it. X would have the smallest radii. Oh, no, no, no. Quite the contrary. Quite the opposite. It would have the largest radii because X is family 1, group 1, and the atoms get smaller left to right. All right, Z would have the lowest metallic character. No, no, no. Z would be a halogen. As we move left to right, we're going from the metals to the nonmetals. So Z would actually have the lowest metallic character of the ones in that row. On the periodic table, the metals are on the left side. The nonmetals are on the right side. So Z would be right here in this thing, family 7. They all have 7 valence electrons. Most of those are not metals. Fluorine, chlorine, bromine, iodine, they're not metals. They're not metals. They're nonmetals. So it would have the lowest metallic character. That's true. Atom Z would have the lowest metallic character. I don't know if I said that wrong. Metallic character decreases left to right. True. What about letter E? X and Y would have a greater tendency to become cations. Yes, yes, yes. If X could lose its electron out of the S, it would leave its inner level full. Group 1, family 1, wants to become 1 plus. Group 2, family 2, wants to become 2 plus. They want to lose these 2 electrons. Z needs 1 more electron. It would want to become 1 minus. Atom X and Y would have a greater tendency to become cations. Absolutely. Z would have a greater tendency to become an anion. Absolutely. So once again, I don't know if I said D wrong. Z would have the lowest metallic character because Z's on the right side. Metallic character decreases left to right. We already did question 40. All of these contribute to electron affinity. Letter E. That concludes the help videos over Unit 5's test, 5-11. If you're confused or have any questions on 5-11, don't hesitate to contact me. I'm happy to go over any of these that might be causing trouble.